Hello, and welcome to our talk on hydrogenation of alkenes. This is part of our unit on addition reactions. So all these reactions are about things you can add to double bonds. But another cool thing about this reaction is it's also a reduction reaction. So you might be watching it for one of those two reasons. In class, we talk more about how to predict the products of a hydrogenation reaction. So in this video, I want to focus more on the mechanisms and how that works and other strategies you can use with hydrogenation. So hydrogenation, as the name implies, is adding hydrogen. We add the hydrogen in the presence of a catalyst, so that's what that PD/C is. It's an addition reaction, which means that our double bond is going to be the nucleophile, and we're going to react it with some sort of electrophile. And in this case, we're adding stuff to both sides of the carbon, so that's in this section, that makes sense. So we talked about adding two things to the double bond, that it matters the stereochemistry in a lot of cases. So in this case, we're going to get the syn addition. Syn addition means you add to the same side. So in this case, we're adding hydrogen to both sides. So if you look at example A, the two methyls are actually already there. So if I number the carbons, they would look like this. So you can see that the double bond was on carbons 2 and 3, and then those methyls are 1 and 4. So there's hydrogens being added, because if you look at carbons 2 and 3 on the left, that already has 4 bonds, so there'd be no hydrogens. So that means that on 3, there should be a hydrogen. Now, if I draw the hydrogen stereochemistry, I would draw it as a dash, right? Because the things in the front are the wedge. That means I have to have a tetrahedral carbon, then I need to have a dash in the back. So it would look like that. You don't have to draw the hydrogens because it's line bond form, so traditionally this is the form you would use for the final product. But if it helps to draw the hydrogens in, you definitely can do that. But the point of syn addition, again, is just to say that the thing that adds on the same side. Syn means the same. So the hydrogens are both adding to the same side, okay? So then if you look at the next reaction, you're actually adding it to an alkyne. And if you look, that looks pretty different. But if I number the carbons again, you can see I've got 1, 2, 3, 4 carbons on this side. And I have 1, 2, 3, 4 carbons on the right side. So it adds to make a double bond first, and then it's going to add again to make the triple bond. So we'll show what that looks like. The cool thing about hydrogenation for a synthetic perspective is that it makes an alkane. So this is the only reaction we know that makes an alkane. So if you see that you want an alkane as a product, this is a great reaction to have. So now that we know what to expect from the reaction, let's talk about what happens in the mechanism. So for this reaction, like we said, we're using a catalyst. The catalyst is this palladium on carbon is what this stands for. It's a metal. So because it's a metal, it's actually doing fairly more complex mechanism that involves organometallic reactions. We're not going to get into that level of detail. So just a disclaimer, we're using the mechanism here just to sort of show an approximation and to help you understand why the thing is syn. So another thing we're going to do is just think about when it's in your head. You don't have to draw this part, but the palladium's holding the hydrogen on the surface. So surface area is important to catalysts, so we know it must be something related to the surface. So think of it as on one side we've got this palladium, it's like a big metal surface, and then the hydrogen is being held in place there, and then the double bond in the solution can come by and get the hydrogen, and the hydrogen's going to stay still. All right, so that's a way you can sort of imagine it. Again, it's a little more complicated than that, but that'll work for now. So for most introductory organic courses, you would not need to draw the organometallic version. You would not need to draw this version on the right. You can draw the approximation on the left, but obviously check with your professor. In my case, this is what we're going to do on the left. So the first thing that's going to happen is we're going to draw hydrogen. So that's just hydrogen, single bond hydrogen. It doesn't have any double bonds or anything. So that's going to be our electrophile, right? Because our double bond is usually the nucleophile. In this case, an alkyne is going to react similarly where the pi electrons are going to be the nucleophile. Okay, so we're going to show electrons coming from the center of the bond, right? And it's going to go to one of the hydrogens, just pick one. And then at the same time, the bond from the other hydrogen has to break because hydrogen's only allowed to have one bond at a time. So we're going to show the bond between the hydrogens breaking and going back to one of these carbons. And that's going to add to both sides of the alkyne at the same time. So when we make our product, we're going to have an alkene, right? Because we've added two hydrogens. Now the question is that going to be a cis or a trans alkene? So what do you think? Well, if it added to the same side, then it should be a cis alkene, right? So we need to make sure we draw that. So when I draw the product, I'm going to draw the alkene and I'm going to make it have this shape where they both point the same direction. So we'll have them both point up since the hydrogen was on the bottom in this drawing. So that's going to be a cis alkene. So it is important that you draw the cis stereochemistry for this intermediate. So then the next step is going to be exactly the same as the first step. We're just going to have a double bond instead of a triple bond be the nucleophile. So we're going to draw our hydrogen again. Maybe I'll stick it on this side just so it makes it a little bit more clear. And then we will attack starting from the double bond to the hydrogen. And then where's our second arrow? Right? It's going to go from the bond to one of the carbons. In this case, it doesn't matter which carbon because they're the same. All right? And then that's our product. That's all we had to do. So when we went from the left to the right hand, we added 2 hydrogens here on carbon 2 and 2 hydrogens here on carbon 3. You don't have to draw those, but that's what we got for our product. So hopefully that makes sense. If you have questions, obviously you can contact me and ask me, but that's all there is to it. It's pretty easy. So if I had to do the mechanism for just an alkene, basically I would do the part here from the middle to the product. So I'm not going to show that separately, but that's what it would be. It'd be just a lot shorter. Okay, great. All right, so let's see one more example of how we can use hydrogen to figure some stuff out. So before I move on from hydrogenation, I want to switch gears for a minute and talk about a special use of hydrogen for determining structures for organic compounds. So this is a little bit of a historic example. So if you look here, what we're going to do is use some information about hydrogenation reactions to figure out if a molecule has alkenes or rings present in the molecule. So if you're thinking back a long time ago, you have some sort of substance, usually a liquid if it's organic, probably pretty volatile, and you want to know what it is. So the first thing you would do is you would burn it because most organic chemicals are combustible. You can burn them, and then by calculating the amount of CO2 and water formed, you can figure out how much carbon and hydrogen were originally in the molecule. So that's what people did first, so they could figure out the molecular formula. Then they would do certain reactions to try to figure out what functional groups were present and things like that. So in this example, you can see the information we're given. So the first thing we know is there's no alkynes present. So that's going to make our calculations easier. So that's why we're doing that part. The second thing we're going to know the original formula. So we're trying to figure out molecule X, and we know the formula is a molecular formula, that's MF for molecular formula, of C6H10. Then when it's reacted with excess hydrogen in the presence of a catalyst, so we put the catalyst in there, that's going to form a different molecule with a different molecular formula. So it's going to make a molecular formula with C6H12. So what does that tell us? So I like to just sort of draw it out a little bit more. So I'm going to show it sort of in reaction form. So we're going from C6H10, which we don't know the structure, and we're going to react it with hydrogen and palladium on carbon, and then we're going to get the C6H12. So what we can do with these to figure out more about the structure is use the degrees of unsaturation, the DU. Remember we did that calculation a while back. So we're going to use that to calculate how many double bonds or rings we might have, okay? So if you remember, the formula for that is 2C plus 2 minus the number of hydrogens minus halogens plus nitrogens, and then all that divided by 2. So that's the formula. If you don't remember the formula, remember you can always just draw an example. So just draw a molecule that's C6 and then count the number of hydrogens and then see if you need to make a double bond or add another DU, okay? So once I've got that, I'm going to calculate the DU for both sides of this equation. So if I look on this side, I've got C6H10, so that would be calculated a DU of 2. So you can use the formula, but that's what it is. And then on the other side, I've got a DU of 1. All right? So we need to know the number of rings and the number of double bonds present in our molecule. So let's start with the rings first. Those are a little bit easier to calculate. We said we have an excess of hydrogen 2. That means we have as much as we possibly would need. So it's going to react all the way with all the double bonds that would be present in the molecule. So we can use that and then figure out if we've got a ring. So obviously if I've reacted all the double bonds, all that would be left over is some sort of ring, closed structure, a cycloalkane. So that's going to be the product. So that means I can figure out the rings based on that. So if I have 1 DU, how many rings would I have? Right, I would just have 1. That 1 DU is the ring. So now that I have that information, I'm going to try to figure out how many double bonds I have, right? How many alkenes. So we know that the total DU of the molecule is over here on the left, right? And then we also know that the total DU is equal to the number of rings plus the number of alkenes. Again, we don't have any alkynes present, so those aren't included in the formula. So then if I know that, I can just do a simple subtraction and take the total number here, which is 2, minus the 1 DU I already have for the ring. And then what's left over is the number of alkenes. So in this case, that would be 1. So that means I have 1 alkene. So often in a problem like this, you might be asked to stop there just at the molecular formula and the rings and double bonds. But sometimes you might also be asked to draw a possible structure. So all you have to do for the possible structure is remember what you did for isomers, and you only have to draw just one. So I'm going to draw a molecule that has the formula C6H10. And then I'm going to make sure it has one ring and one double bond. So I know exactly how many it has. I can't just like make up anything I want. So then you can draw an example with that. So one example I could do is I could do a 6-membered ring. So I could do a hexagon and then add one double bond. I could do a pentagon and add one double bond. I could do a square and add one double bond. I just need to make sure however many I have that I add the other carbons that are missing. So for the C6, I can't add any. For the C5, I can add one methyl group, so you can add it pretty much anywhere around here. And then for the square, obviously you have to add 2 carbons. So you could add 2 methyls or you could add an ethyl. So hopefully that makes sense. Any of those answers would work for that one, right? So as long as it meets the criteria of one ring, one double bond, and has the right formula. And remember to check any sort of thing like this. You always want to just double check by counting the number of carbons and the number of hydrogens. So you don't have to just count on math. You can actually just use counting to figure out if your answer makes sense. Okay? So that's all I have to say about this. And with that, we will conclude this video about hydrogenation. Make sure you check if this is part of a series. You might have another video to watch today. But if not, you can go ahead and check Blackboard or your course website and see if there are any activities for you.